with that said, just wanna okay. So now that we have done this, I just want to put forward a very, very important thing here. Now, we're going to look at the path of a moving charge in vacuum and in a gas. So suppose we have an infinite field that's into the page, just like we had one before. And copy this. So there could be two conditions, right? So there could be air resistance or there could be vacuum. Sometimes it's not even air, there's some other chambers, so there could be gas resistance as well, because there could be any gas. So when a charge basically enters, suppose the charge is positive, so you know the velocity is here, you can find the force. So the charge will basically go in circular motion, but because of the air resistance, it is going to retard as well. And slowly it is going to just end up at one point and stop, because air resistance is acting this way. Is it clear, everybody? However, if this was in vacuum and the field is there, then the positive charge, whatever charge it is going to continue moving in just one big circle forever, because it is not going to lose its speed, and now there's nothing to defy it, and that's why it's just moving in a circle. Is it clear, everybody? Now there are two facts that I want you to understand very, very clearly. I'm going to write it. Number one, the main difference between a magnetic field and electric field is that in the magnetic field, force is experienced by only moving charges, and you just need to remember that always. Okay, if the charge was not moving, it was put in the magnetic field, nothing will happen, because when the charge moves, it creates its own magnetic field that interacts, that we've learned. But if it's not, then there is no force at all. The other thing you guys need to remember is that in electric fields, force is experienced by static and moving charges both. So both of these charges, whether it's static or it's moving, they will both feel a force depending on their charge all the time. Is it clear, everybody? Any questions? Please let me know. Okay. Now, so keeping that in mind, let's do a question and see whether we do understand that, okay? So the question says, for example, an electron travels from the left towards right. So they've actually given you this. In a magnetic field with a velocity of v and adopts a circular anti-clockwise motion. It says if the strength of the field is 2.1 Tesla and velocity of travel is 12% of speed of light, my bad. So number one, you got to determine the centripetal force. Number two, determine the radius of curvature. And number three, draw the magnetic field lines. Okay. Now that is the question. Okay. So first of all, let's think about it. If you go to what we have studied up till now, you might realize that in a magnetic field, the charge basically moves in a circular motion. And the force that basically enables it to do so is basically the magnetic force that is always present and is acting right angles to the direction of its velocity, that basically contributes to the centripetal force that causes it to move in a circle, right? So that would mean that actually the centripetal force would be equal to the magnetic force that is acting on a charge that is moving in a circle. Now, because there is a single charge, Suman, can you please tell me what is the formula for that? Force on a moving charge? Yes, Suman. Don't remember? Gatika, you remember? Asanti?
Yes, which would be BIL.
BIL is the force on a wire. BQV it is the one. Gatika, that is for the force on a single wire or a wire. So that is going to be F equals to BQV. You already know this. So you have 2.1 Tesla times, what is this? This is an electron. Do you guys know the charge on an electron? 1.6 times 10 raised to minus
10 raised to
19.
minus 19.
Yes, very good. So 1.6 times 10 raised to minus 19. And then the velocity is 12% of speed of light. 12% is basically 0.12, and the speed of light is 3.0 times 10 raised to 8 meters per second. I'll write it right here so you guys remember this. Okay. Alright. Now that's pretty cool. Let me see. Oh, hello Ramin, how are you? Is it Ramin or is it Ramin?
It's Rami.
Okay, Ramin, how are you? Do you understand what we're doing?
Yes, sir.
Okay, good. So then what you're gonna do is when you find this out through calculator, you're gonna get 1.21 times 10 raised to power minus 11. Please do confirm this answer because of course some of my students have done it and I put it down here. Okay, now then it says determine the radius of curvature. Do you guys know how to do that? The hint is that this formula basically includes momentum as well. Can you please tell me now? No? That's not fair. So you go back. Do you guys remember this formula? Yes. Now you're gonna write this down. So radius of curvature is given by R equals to mv over bq. Now check this out, please. The mass of an electron basically is, I remember this as 9.11 times 10 raised to minus 31 kilograms. So we're gonna put that down. And then the velocity is 0.12 of 3.0 times 10 raised to 8 divided by the magnetic field strength is 2.1 Tesla and the charge is 1.6 times 10 raised to minus 19 coulombs. So that's as simple as this. When you do that, it's gonna give you 97.5 times 10 raised to minus 6 meters, which is basically essentially equal to 97.5 micrometers. Is it clear, everybody? Let me know if you have a question here. Okay. Cool. Now the most interesting question is the last one, because here what in the question it says that electron travels from left towards right, okay, in a magnetic field with a velocity of v and adopts a circular anti-clockwise motion, which means that actually if you draw the path of an electron, so it should look like something like this, and it's going anti-clockwise like this, and this is basically an electron. So we want to draw the magnetic field. Now the best way of doing this is the only way, right, so it can move like this is because it would mean that each point its velocity is going to be tangent to the circle like this, and like this, and like this. So we have the velocity, and now because it is electrons moving like this, we got to use Fleming's left hand rule. So I just want to tell you one thing very important. Fleming left hand rule is basically used for positive charges. So when you have the current, so it's basically used for positive charges moving in a sort of a current. So this means that whatever it will show you for this one has to be in the opposite direction. What I mean by this is, let me just tell you. If it is going in a circle like this, it means the force that is basically acting on this should be towards the center. So this is the force, and force, because it will move in a circle, right? So we have the direction of the current, we have the direction of force. Now we got to use this. Can you please tell me where the magnetic field lines are going to be? Please use the Fleming's left hand rule. You can actually pick any point that is,
Sir, into
suitable.
the page.
Into the page? Okay. So if you place your thumb, like let's look at this point, okay? This point. If you place your thumb upwards, so that's your thumb, and you place your middle finger just where the velocity is, right? So this is your middle finger. So where is your index finger? Please tell me.
So into the page.
Into the page. So there is, the index finger is right into the page. We do understand that. But that is only true for the positive charges, because we have an electron here. So electron would move in this direction only when, it's very important, only when the field is out of the page. Do you guys understand this? So whatever the Fleming rule is telling you, for the negative charges you just do the opposite and it will give you the right answer. Do you understand, everyone? Suman?
Sir, also, in the
Yes.
question it specified that it's adopting an anti-clockwise path, right?
Yes, it is specified.
So, sir, फिर आपने बताया था कि anti-clockwise में फिर magnetic fields and field lines are out of the page.
No. Did I say that? That must be something else, not this. Currently,
So you said something like that.
field is out of the page. No, I just,
Let's look.
you can check from behind. What I'm saying is that if you use Fleming's left hand rule right now, the magnetic field direction is coming into the page, and that is true for a positive charge. But because we have an electron that is a negative charge, we are just going to reverse whatever our finding is. So if it was into the page, according to the rule, for the negative charge, it is going to be out of the page now. Is it clear, everybody?
Yes, sir, for linear conductors जहाँ पे आपने लिखवाया था.
Linear conductor is right hand grip rule, beta. This is not related to that.
Oh, yes, sir, okay.
Right. Okay, Hasan Atik, do you understand? And about Rafe and Ramin.
Yes, sir, understood.
Okay. Gatika, is everything okay?
Yes, sir.
Okay, that's cool. So now you guys understand when to use what. Okay, do remember that point. That's why I put this question intentionally, so you don't make a mistake here. Now back in O levels, you used to learn about the influence of one current carrying conductor on another. Okay, and I'll just remind you this, and you will be like, oh yeah, we studied this. So you might remember that your teacher at that point in time, they might have told you that when the current in wires are going in a similar direction, so let's suppose this is current 1 and this is current 2. So current carrying wires in the same direction basically attract each other. Remember? Because they feel a force. And current carrying wires in the opposite direction, they repel each other. For example, let me put it here so you guys remember. In O levels, we studied that like currents attract and unlike currents repel. But the thing that we never learned there was how and how much force is there and how to calculate that. We just learned that okay, this is the force. Okay, so let's see. Okay, now. So, speaking of that, then, let's look at an example and try to understand what basically I mean here. So, the example is like this. Suppose there is a wire that's carrying current in this direction. Okay. And now, because the current is going up, so the magnetic field basically goes like this. Concentric circles, please, like that. And at one point, like really somewhere here, okay, we're checking an effect. So there is another wire that is basically placed at this point. Let me put a dotted line, and let's call this point as x. Okay, and this distance from the wire till the other wire, so this wire I to this is 2 centimeters. They say the current in this is 6 amperes, and now the magnetic field from the grip rule, we already know it is going to be going like anti-clockwise, just like this. Okay, in 10 minutes please rejoin the same link, okay, when the meeting ends. Now the first thing I would like to know is, I would like to know the magnetic field strength. Usually in the exam they're going to give you the equation themselves. I'm going to show you the question soon. So magnetic field strength is basically given by, I've also given you this equation before, if you go back, scroll back. So for a single wire, where it was here, I told you the magnetic field strength is given by mu naught I over 2 pi r. So usually they will give you this equation themselves, so it's fine. So mu naught I over 2 pi r basically give us the strength at x. So we're going to look at magnetic field strength at x, where the other wire is. Okay, now please check this out. So if I put the values in, so magnetic field at x is going to be mu naught is basically 4 pi times 10 raised to minus 7. Nobody is going to tell you this, so you got to remember this. And this value is not even given in the data sheet, so you have to remember this. The current in the wire was 6 divided by 2 pi, and the distance is basically 2 centimeters from the center of the wire that's carrying current to the other wire, which means we're going to write 2 times 10 raised to our minus 2, like that. Okay. All right. So then we're going to look at this, and if you find this out, this is going to come out as, oh no, let me put it to charge. Wait a second. Okay, so if you look at it, this is going to come out as 6 into 10 raised to power minus 5 Tesla. That's the magnetic field, right? Now, if you notice, if you look at from the very, very front, right? So right here, if I just point at X, you might realize that basically the field is coming out of the page from that point, which means this is the strength. I'm going to say at X, the field is out of the page, and you got to basically look at from the drawing. So the outer page means that it is going out of that point. So if you look at in 2D, it's coming out like that. Everybody agrees to this? Any questions? Please let me know. Now, so the next step you're going to do is you're going to find the force on another wire at X. Now check this out, please. So the other wire, suppose that this wire is given like this. It means that basically the magnetic field at that point is going out of the page like this. Okay, this is just to explain it to you. Whether you draw it or not doesn't really matter. Like this. And they have told you that this wire is basically carrying a current upwards of 4.8 amperes, and the length of the wire that is affected by the magnetic field is 1.2 meters, which means that basically this length that you see is 1.2 meters, and the current it's carrying is 4.8 amps, like that. Okay, now once you have the magnetic field of wire 1, so what you're going to do is you're going to use F equals to B, I and L to find the force. Now the magnetic field at X was 6.0 times 10 raised to power minus 5. The current in the wire was affected by the magnetic field is 4.8, and the effective length is 1.2. Affected means that it's basically touching the magnetic field there. So it is going to be 3.46 times 10 raised to power minus 4 newtons. Is it clear, everyone? Okay. Now, interestingly, I'm just going to prove what your O-levels teacher told you, because he was actually right. If I ask you, looking at this diagram only, if I ask you where exactly is the force, so you got the magnetic field direction, you got the current, which rule should we use to find the force on the wire? Anybody can explain this to me? Yes. What do you guys say? You got the magnetic field direction, you got the current direction. Can you find the force direction? What rule will we use?
Fleming's 15 rule.
Yes. Can you do it and explain it to me? How, where would the force be? So the force direction can be found using Fleming's left hand rule. Now check this out. It means your index finger should be coming out of the page. So that's your index finger. The middle should go up because that's where the current is. Now, where is your thumb, please? No idea?
So left.
Left or right? I think it should be right.
Towards the right.
Someone do it again. It should be here. Check.
So index finger out of the page, right?
Index fingers towards the current. Oh yeah, sorry. Index finger towards the out of the page.
Yeah, so
Middle
then it's right.
upwards, and then it's right. Okay, so the force direction can be found using Fleming's left-hand rule. In this case, it's towards the right. Okay, so on this diagram, can I say that this means the force is going to act like this? Okay, now we clearly understand the force on X is towards the right. Then what can be deduced on the force on the wire that's carrying 6 ampere? So they're going to ask you this: what will be the magnitude of force and direction of it on wire carrying current of 6 amperes? Okay, so this is the wire. Can somebody please make a wild guess here? You don't need to calculate anything here. You just need there's a law of physics that tells you about a force. Yes, who's going to tell me that? Now think about it in this way. If wire 1, which has a 6 ampere current, applies a force F of the value 3.46 times 10 raised to minus 4 on wire X to the right, what will wire X do? Something that Newton has told us. Something. Recall, please.
So it will exert equal and opposite force.
Yes, very good. So it means that the answer to this question is going to be that according to oh no. Okay. Okay. All right, we're back. So then, according to Newton's third law, we're going to write it like this: wire X will apply a force of 3.46 times 10 raised to minus 4 newtons to wire carrying 6 ampere current to the left. Is it clear, everybody? Now, the real difference between how you would write things in O levels and how would you write things in A levels is that when you're explaining Newton's third law, you gotta basically point the two objects that you're talking about in your answer. Okay, so because we knew from the previous like parts that we've done that because the force on X was towards the right, so I would say the force on the other wire would be towards the left, and I would also state the magnitude. I'd say it's a equal magnitude. Is it clear, everybody? Just don't write that there will be an equal and opposite force, because then it would not make sense to the examiner. You have to explain it properly. Is everything clear? Any questions? Okay. Now we do the same thing for another wire, and this time I expect you guys can do this. So I'm just going to write.
Sir, how did you know at X the field was out of the page?
Because when I drew the magnetic field, right? If you look at this magnetic field, this goes like in from, it's an anti-clockwise field, right? So Gatika, it's coming out from this side, from the left side, right? So if you just look at where the red circle is, if you look at it from the front, don't you think it's coming out towards you?
Yeah.
That's how I know, by drawing that field. Understood?
So if you take the arrow on this side, then it's into the page?
On the other side?
Yeah.
Yeah, it's into the page because it's going away from you. Okay? Right. So now let's go to example 2. So now in example 2, I want you to basically, they've shown a wire that's infinitely long wire, and it's carrying a current of 3 amperes. Okay, so let me write it here instead of 3 ampere. And there's another wire which is not infinitely long, this is just here, and this wire is carrying the current in the opposite direction of 4.8 amperes. So let's call this I1, let's call this I2. And then they've also given you the length of the other wire, which is primarily 3.2 meters. Okay. They've also given that this distance from the center of this wire to this wire is basically 0.25 centimeters. And you have the currents, you have the direction, and now they say find number 1, strength of the magnetic field, on wire I2 by I1. Okay, the formula is given as B equals to mu naught I over 2 pi r, and then in the second part they say find the direction and magnitude of force on wire I1. Okay, so you just need to do that. And in the third part they say on figure draw the direction of force acting on I1, I2, sorry, I2 by I1. Yes, that's what you're gonna do. Can you please do it? It has the same method that we've followed. Okay, you just need to draw that. Can you please try and do this? By the way, if you don't remember, well, you should, but if you don't remember, mu naught is given by 4 pi times 10 raised to our minus 7. So you just need to remember that. Okay, can you please do it now?
Sir, can you show example 1 again?
Yes. Have you copied this?
Yes, sir.
Okay. This is the example 1.
Alright, sir.
Go on. Hello Fatma, how are you?
I'm good. How are you?
I'm sorry I joined very late.
Yes, it's the end of the class now, Fatma. Fatma, you
Oh,
can find this on
no
YouTube as
problem.
well, okay? Yeah,
Yeah, okay.
okay.
Do you have the recording though?
It's being streamed right now. Okay. So
Okay.
before you join the next class, make sure you watch
Mm-hmm.
the stream, okay? So you're updated. Otherwise, you'll be like sitting ducks here. Okay, Fatma?
Okay, fine.
Okay, you can
Fine.
still, chill and see what we're doing right
So
now.
should I leave?
It's up to you. I mean, you can sit and you can, watch for another 5 minutes, or you can just go and check the recording later. Okay? It's up to you.
Okay. Yeah. Thank you.
All right. You guys, done? Please don't say that.
Yes, sir.
Okay. All right. Let me. Oh, wait. I don't want to save this thing. Okay, I'm just giving 2 more minutes to you people. And then we are going to check what we've been doing. What do I have this? Okay, I have a basic class after this. Fine. Okay. Now, Suman and Ramin and Aman, you guys also done? Rafe, about you? That is stuck. Okay. Now, can you please give me an answer here? What did you guys get for the first one?
So
Go on.
is it 2.4 into 10 raised to negative 4?
That's correct. And for the force?
3.68 into 10 raised to minus 3.
Yes, that's correct. Okay. All right, let's see this. So what we have done here, what she has done actually, is that using the right hand grip rule. So basically, when you put your thumb like this and then you grip it like this, okay, using your fingers like that. So the magnetic field would basically be like this, okay, like that, a clockwise direction. And of course, at one point, like, I don't know, my page limit has ended for some reason. Okay, here. So at this point, the magnetic field is basically going into the page like this from here, because it's clockwise like this. Oh no, wait. Yeah, this is anti-clockwise. Okay, like that. And it means that basically now we can find it through this formula. We know it is 4 pi times 10 raised to a minus 7. The current in this wire, which we're looking at, is 3 amperes divided by 2 pi, and the distance between them is basically 0.25. Because it's centimeter, I got to change it into meters like that, and I'm gonna get it as 2.40 times 10 raised to power minus 4 Tesla. Alright, you guys understand this? Raman?
Yes, sir, understood.
Okay. Then, to find this, we got to use F equals to B, I, and L. If you look at what is happening right here, you might see that this is the wire I2, and the field is basically going into the page from here, as you can see in the diagram. It's going away from you, and the current is basically down here, which is 4.8 amperes. So I'm going to use the magnetic field at that point was 2.40 times 10 raised to minus 4. The current was 4.8, and the effective length was basically 3.2 meters. That should give me about 3.69 times 10 raised to minus 3, which can be written as 3.69 millinewtons, right? So we got this. Now on the figure, how would we do this? Now if you check this out, you say that the magnetic field is into the page, which means the index finger of will be inside, the middle should be down. So this is index, this is the middle. So you'd realize that basically your thumb is going towards the right. It means this force, this wire will actually feel a force towards the right. And because of Newton's third law, if I2 forces I2 towards the right, so I1 will be forced by I2 towards the left of the same value, and that's what you got to do. Understood?
So can you repeat the last point?
Yes. So what I'm saying is that if you look at it, your index finger, which is the direction of magnetic field, the index finger should be into the page. So this is your index finger. You turn your wrist in such a way that your middle finger is towards the current, which is going down. So this is your middle. And then you'd realize that your thumb is basically right here, right? Which means that the I2 is being forced towards the right. You agree to this?
Yes, sir.
If I1 applies a force on I2 towards the right, then I2 will apply a force on I1 towards what?
Left.
Left, and of the same value. That's why we drew this force here. Understood?
So we only need to show that one arrow.
Yeah, we just need to. I just do it for you. Okay, that made it. Happy? Okay. Alright. Is it clear, everybody? If you have any questions, please do let me know. Otherwise, I will see you tomorrow, same time. 6:20 Pakistan time. Bye. Have a nice
So I
day.
have a question.
Yes, Fatma.
I have a question. So, you guys already covered the first few chapters?
Yes, we have.
You guys have already covered, so you're not gonna review it again?
We
Like
are
a new
going to
series?
review it, Fatma. Why not? Basically, I'll tell you
Oh,
what.
okay.
A2 has every chapter is different from others, okay? So
Mhm.
you can actually start A2 from the end towards the beginning or from beginning to the end, okay, Fatma?
Okay.
So because you joined now and this session was
Yes.
like started in June, so I would say you continue with this, okay? In December we're going to end the whole syllabus, and in December we're going to restart it. Understood, Fatma?
Okay.
So that
Got
way
it.
you will be able to cover all the syllabus. Otherwise, if you join another session right now, it will be waste of your time, as it will be too fast for you to understand. Understood?
Okay, right.
Yeah. So save your time, please.
Right.
All right. See you then, my people. Have a nice day.